Thank you all for joining and giving me this opportunity to share my perspectives on laser-resisted additive manufacturing, and also as an extension from our surface engineering initiatives for the last several years. Prakash already mentioned, I am associated both with currently at the Birla Institute of Technology, Mesra, Ranchi in India, and I've been associated with IIT Kharagpur for the last over 4 decades by now. It's quite a long time. I must also mention that my association with laser started primarily as a tool for surface engineering, started somewhere in mid-90s, 1994, 95, when I had an opportunity of spending half a year at the University of Liverpool, not too far from here, under the guidance of Professor Bill Steen. And since then, I have always worked in collaboration with various institutions who have had laser machines. And I was finally fortunate to have a laser machine, a fairly 6 kilowatt multi-axis forward delivery system installed at IIT Kharagpur in 2019. So since then, we have this unit through which we can do both surface engineering and additive manufacturing. And very recently, last year, we got one machine installed at Birla Institute of Technology, Mesra, which is instead of wire, it feeds, instead of powder, it feeds wire. So it's an additive manufacturing unit with a wire feeding arrangement. Compared to the conventional manufacturing, which usually produces a large amount of waste or scrap at the end of the manufacturing cycle, in additive manufacturing, you actually tend to have just a reverse cycle where you start with powders, for example, as the feedstock, or whatever is your feedstock, and you end up with the final product sparing very little waste, practically zero waste. So this is much greener and much more economical way of producing. The advantages lie in these 4 or 5 main points. You can design the entire product completely on a digital platform, and hence you can tailor, change, or modify at your will at any point of time. So you have immense flexibility, precision, accuracy in terms of the dimensions, in terms of even microstructure and properties. So you don't need expensive, like you're doing manufacturing moldless without the need of having any mold or fixtures created for that. So completely green and clean manufacturing approach, and metals for sure, polymer obviously, because the entire additive manufacturing process started with polymer as the feedstock material. Ceramics is quite possible. In fact, only the other day I just saw myself a big cement block, a concrete block, prefabricated concrete block manufactured. But when you talk of neutral oxides like alumina or several others, zirconia and so on, this is still not so well established. So ceramics still is something to be worked on, but metals and polymers for sure. But you do either complete manufacturing, a complete product with a required dimension, or you certainly can do repair, refurbishment, replacement, and so on. So in my opinion, additive manufacturing at the moment is much more applicable and suited for high cost, low volume products. In other words, you won't be competing to create the bottle cap by additive manufacturing, because it will take much more than just a stamping operation. On the other hand, you don't mind spending any amount of money, and even if the order is only for one single piece, if it happens to be a heart valve or a prosthetic implant or a very specific component of an aircraft. So high cost, low volume products are the key targets for additive manufacturing. But just like any other engineering efforts, there are the flip sides. For example, you have certain size restrictions depending on the machine that you are using. If you're dealing with powders or, for that matter, even other feedstocks, you're likely to develop products with certain level of porosity and an isotropy because of the direction in which you are manufacturing that gets embedded in the product. It's not always suitable for non-weldable solids like the ceramic oxides that I just now mentioned, for glasses, for example, and not competitive for mass productions. But the most important thing is that though the mechanical properties we claim lying somewhere in between a wrought product and a cast product, so strength or toughness wise. But what probably is not well established is the long-term performance of these additive manufactured products. For example, mechanical behavior in terms of fatigue or creep or maybe even high strain rate deformation situations and so on. So these need to be assessed over a period of time. So this is the overall scheme, and this is all very much available in the internet sources, so I don't need to repeat all of them. What is important is that we can take three specific approaches: the liquid-based approaches, where the feedstock is actually dissolved solution, or maybe a liquid polymer, or solid-based products, where we integrate laminates one after the other of a particular geometry. But more popular is powder-based techniques, where we either melt or we simply bind in with certain binders. And in the process, we can produce three-dimensional products. So in a typical powder-based approaches, one would like to possibly fill a tank with certain volume of powder, then use a certain leveler to make the surface flat and smooth. The powder size can vary from micrometers to millimeters even. And you can also mix different types of powders, but the bed has to be a sort of compacted bed. And then when you have a laser shining over the particular powder bed, then you melt only a certain directed region and not the rest. And you move either the beam or the bed, whichever is suitable, on the table, and then end up with a particular shape. And when you build that shape, we have to realize that you build layer by layer. So this is the process integration will require, for example, if you're doing with a point source like this, there's a pointer, then you'll move initially along, let's say, X direction, and then shift by a certain level to certain measure to Y, and then again repeat. So you build one layer, for example, one layer here, and then you go back and build another layer and so on. So when you keep building layer after layer, you need not fill up the entire layer. So in between, you can leave a gap, and in the process, you can create a hole like this or a hollow section like this. You can change the geometry. It need not be exactly the same dimension. So in the limit, you actually can develop much more complicated shapes like this, provided you have taken very precise two-dimensional sections and digitize them into the digital files which can be fed into the machine. Just like typically what is done in a computer-aided manufacturing process. So I have a big list here. These are all variants of various additive manufacturing approaches based on laser or based on polymers and various other jet feeding arrangements. And there are different names. I mean, they're just, as I said, variants. Now, instead of directed energy beams like laser or electron beam, one could also use, for example, layered objects and weld them together, sheet by sheet, or can actually deposit liquid metal or liquid polymers into a particular region and then allow them to take a particular shape. So I'm just skipping all those details. What is important, I mean, why we pay so much attention is simply explained by this view graph here. So if you do machining alone, then the energy that you consume for a particular component so typical conventional machining would require a much larger energy. Compared to that, when you have a wire-fed direct energy deposition or laser powder bed fusion and so on, this is almost like 1/5 or maybe an order of magnitude lower. So which says that this is a very energy economy process. And what is even more important is that if you look at this graph, so the billions of dollars, the market size in terms of billions of dollars, and over the time period that it's actually growing. So let's say if it started somewhere around mid-90s compared to that when the total volume was just a fraction, maybe $0.1 billion or $100 million or something like that. Compared to that, until about 2018, 7-8 years ago, it rose to almost $10 billion. And today, almost 16 to 20% of the market is occupied by the aerospace and defense industry, various products which are routinely used, which are made by additive manufacturing. And the business in just about a year ago rose to double this amount, $20 billion, and it's projected to reach 88 plus billion dollar by 2030, in 5 years from now. Almost 5 billion parts will be manufactured of various types, not the same parts 5 million times produced. 5 million varieties of products will be manufactured by additive manufacturing, which shows almost 23-25% increase in terms of the importance or the variety that it can address to globally. And in India alone, if it is somewhere around 0.6 billion of business now, it's going to grow 6-7 times in another 5 years. So that's the huge reason, huge impetus as to why additive manufacturing is so important. Now, there are two main reasons as to why this approach is so much popular. Number one, you actually can, the entire unit cost, for example, as you can see here, unit cost as a function of complexity. If it's conventional process, then as the complexity increases, the cost per unit increases. In additive manufacturing, since the product is completely digitized, so you can change it at any point of time, whether it's very simple, like a simple rod, or a very complex spiral shaped with hollow sections inside. Irrespective of the complexity, the cost per unit remains nearly the same. So that is one of the biggest advantage. And the other advantage is that the number of parts, whether you produce 1 or 1 million, is not going to change much in case of additive manufacturing. Whereas in order to reduce the cost per unit in conventional approach, you need to produce a large number. So that's why I was saying that a bottle cap, if you are producing a few tens of thousands a day, then obviously it can be much more cost effective. And there, additive manufacturing need not compete. But if you're producing a few of the components or a few of the parts, which are of very high complexity and importance, then you don't mind paying certainly a large amount. And this is where additive manufacturing comes much more handy. So these are various examples, and the market share, consumer products 13%, industrial products typical about 20%, medical and dental 11%, automobile is almost 20%, so is aerospace about 20%. So these two together actually are the largest reason why additive manufacturing is being so popular. One of the other advantage from the industrial point of view is that you don't need to maintain a large warehouse. So you just know such component is to be built as a replacement or a new component. The order is placed, and within a day you can deliver from wherever you are able to manufacture from the nearest point of view. So large companies, automobile companies, has invested a lot in 3D printing or additive manufacturing so that they don't have to maintain a big warehouse or spend a lot of money in maintaining those manufacturing centers. So now let me move on to the, so this was more of introductory discourse as to why additive manufacturing is so important and is assuming greater and greater importance. So quick few words about laser. So we all are aware that this light amplification by stimulated emission of radiation is a directed beam which actually excites electrons on in the solids of two types. If it's metallic or with no band gap, then the transition is only intra-band. So you have sufficient number of electrons in the conduction band, which immediately are excited and de-excited, and in the process you can absorb the energy. Or else if you have solids like insulators or semiconductors and with a finite band gap, then you have to lift the electrons from the valence to the conduction band, and that's how you can absorb the energies, no matter whether it's actually overlapping or finite band gap materials. The entire process of intra-band or interband transition and subsequent absorption of energy is very fast, in the order of nano to picosecond. So as a result, you actually absorb the energy in a shortest possible time. The advantage is that compared to electron beam or ion beam, the laser energy deposition follows an exponentially decaying profile, which means that as a function of depth, the energy is absorbed highest at the surface and then it decreases very soon. So the entire energy is absorbed primarily in the near surface region. And with this coherent monochromatic low divergent beam with a very high power density, we actually can play with only two independent process parameters, the interaction time and the power density. And by virtue of controlling these two or selecting these two in the right combination, you can do processing only in the solid state, involve melting followed by solidification, or go into the vapor state and then deposit and form a solid layer. So in the process, I mean, what it means essentially is that you can deal with solid without melting, you can melt and solidify, or you can deal with very high melting solids, take them to the vapor state and deposit as a layer or a film. So when you do such processing, you have these following possibilities, two aspects to be taken into account. One is that if you're approaching the entire process through an equilibrium route, then these are the various processes, then you have certain difficulties there. I will come to that in a minute. In order to overcome those, you rather choose non-equilibrium route, where you actually can achieve certain properties which is not possible in equilibrium route. Now, the two major constraints that we have to keep in mind, and which is why we are more interested in non-equilibrium processing, is because of the solubility limit, the equilibrium limit, and the kinetic constraint, the diffusion coefficient restraint. Say, for example, if you're dealing with either solid for sure, in liquid state also, there's a finite rate at which the species can move around, and then in the process they can change their configuration, undergo transformation, phase transformation or change of state, and also allow homogenization of the species that you're dealing with. So diffusivity is a function of temperature, proportional to temperature. We have to keep that in mind. And we also have to keep in mind that there's a limit in terms of equilibrium, which is allowed for a certain amount of solute to be dissolved in solvent. So we actually can overcome both these constraints to a large extent if we can use certain non-equilibrium processing routes, particularly using laser or any such directed energy beam. Now, this is also borrowed from the internet source, so all of you probably are aware that there are 7 main approaches by which you can do additive manufacturing. And these probably are known to all of us, that when you're dealing with polymers, you can do vat polymerization using a photo activation, or you can do material jetting or extrusion, and in the process you can produce such complicated structures. But if you're interested in metallic parts, then you start with binder jetting with certain additives associated with it. But otherwise, you can do powder bed fusion, sheet lamination, or direct energy depositions. So in this, there are 2 major approaches. One is a powder bed, which I alluded to at the beginning. So you have a tank, you fill up the tank with the desired powder, and this could be an elemental powder or an alloyed powder or a mixture. So you can even make a composite. You even can make a porous product out of this if you have foaming agent. So you fill up the tank and then you move the beam from one end to the other in a spot, and then integrating the spots into a line, and then move across and then keep repeating, form a particular layer, and then you raise the layer and make it a 3-dimensional product. The other possibility, which is from the research point of view or from innovation point of view is more exciting, is the energy deposition unit. Direct energy deposition unit. For example, you imagine this to be a nozzle. In real time, the nozzle looks somewhat like this. So in this nozzle, the central part, you have the laser coming right to the middle of the nozzle. And coaxially, you have feeder channels through which you feed powders, and you shield them, cover them up with certain shielding gases to maintain or to prevent undue oxidation. And as you can see, the powder gets interacts with the incoming laser beam in flight, gets molten, and then gets deposited onto the surface. So this is how you develop a layer. But actually, the way you will develop the layer is so-called point or droplet integration. Because at a time when the beam interacts with the incoming stream of powders, it melts only a small volume, and that gets deposited. And then when you keep moving this over a surface, it actually forms a line. And then if you integrate number of lines on the same plane, you make a layer or a plane, and then you lift the focus by a certain amount, you go to the next layer. So that's how you can make a 3-dimensional product. So the biggest advantage of these direct energy deposition approach is that you can play a lot more to modify or tailor the microstructure and composition, and you can make them even graded and create very many interesting components and structures. So this is what I mentioned at the beginning, that with the generous funding from Department of Science and Technology in India, we were able to establish a 6 kilowatt, 6-axis robo delivered and a power delivered system in 2019. It's a complete system which actually can take up even industry scale operations. And as I said, we have a robo to maneuver, we have a powder feeder to deliver powders between hoppers, and control systems. So now on to my specific examples, and I should upfront declare that much of these are borrowed from surface engineering or surface cladding approaches, and but I firmly believe that from rapid prototyping to rapid manufacturing, and finally on to this additive manufacturing, the journey actually started with surface engineering. And when we understood that instead of one single layer, if you can continue to build layer by layer, you end up with a 3-dimensional product, and that's the precursor. So surface engineering or surface cladding can easily be considered to be a precursor of the current additive manufacturing operations. So the first example I want to draw your attention to this marvel called jet engines, aeroturbine engine. You have this large compressor region and combustion region. And in this combustion region, you have the blades which actually experience a temperature in excess of 1000 degrees. And that's where you need to prevent many other threats, One of them is oxidation. And typically this oxidation is prevented by way of a coating, which is a ceramic coating on the surface. But this thermally grown oxides are the oxide layer which starts building at the bond coat, which is metallic, between the bond coat and the top coat, which is ceramic. So prevention of this growth of this oxide layer is a very important exercise. And typically these are done by way of such oxide coating. Now, just to tell you that one of our students, Manoj, developed this kind of, he argued that instead of typically only relying upon yttrium-stabilized zirconia, he varied the level of addition of gadolinium oxide, GD2O3, and he showed in the process. So typically this would be the cross section. This is the top coat, the oxide coat, which is a thermal barrier coating, a bond coat, and then a substrate. And he was able to show that by way of substituting some of the yttria or the zirconia in the zirconia matrix with gadolinium, the same trivalent cation, you actually are able to reduce the thermal conductivity significantly. And as a result, the growth of the thermally grown oxide actually is reduced significantly. For example, as you can see, this is the TGO thickness as a function of oxidation time. And you see the bottommost layer is with 15 mole % of GD2O3 added. And this shows the slowest kinetics of oxidation, which means the oxidation resistance is the largest. So these are various kinetic data analysis to prove that it's indeed very effective. And also it shows higher erosion resistance with this red curve here. Now, the whole exercise, from there, we shifted towards, we raised the question as to why would we entirely depend upon oxides? Why can't we do it with metals or intermetallics? And the clue actually can be obtained from an exercise that we published many years ago, almost 25 years ago, through Josna Datta Majumdar's PhD thesis. And there we showed that when you develop such highly dense silicide microstructure, silicide embedded microstructure, using laser was advantageous because we could develop hyper-eutectic microstructure with much lower solute content of silicon. So this is basically on titanium blade material, and using silicon as an alloying element, though the amount was actually fit to be said hypo-eutectic, but the kind of microstructure we developed can easily be seen as a hyper-eutectic microstructure. Silicide phases, which are congruous, which have a very high congruous melting maximum and are very oxidation resistant, so they make up almost 80 to 90% of the entire surface. So they cover the surface either as these primary phases or as part of the eutectic. And as a result, if you compare the oxidation kinetics of pure titanium as this one and the alloyed layers, which are bottom ones, you can see there's a significant difference in the kinetics of oxidation. In other words, these silicide layers like this are very effective in preventing oxidation of the base metal, which is titanium in this case. So borrowing from this clue, Manoj again tried to alloy silicon, aluminium, or zirconium diboride on Inconel 718. And so this is the cross-sectional microstructure, and this is the top microstructure. And when you look at these oxidation kinetics curves, the mass gain as a function of time, you realize that this bottom curve, the blue curve, is Inconel 718 surface alloyed with silicon. And that makes so much of a difference between the as received Inconel 718, which undergoes oxidation at a much higher rate compared to this surface alloyed. So he did the usual analysis of understanding the phases which are present after oxidation and before oxidation, and the morphology of these oxides on the surface, their thickness and their phase distributions and so on. So what is really interesting here is that if you are careful, you'll be able to see a number of intermetallic phases are still remaining with large peak on the surface despite 100 hours of oxidation, which proves that even after 100 hours of oxidation, you don't have the surface entirely covered by oxides. You still have these intermetallic phases which are preventing further oxidation. So they're very effective in preventing oxidation. So he did a very careful analysis of going layer by layer. So taking serial sections parallel to the surface at certain micrometer depth. So first layer, second layer, third layer, and so on. And in all these bar diagrams, you'll see composition as for various elements, composition for various elements, if it's silicon alloyed or aluminum alloyed. And then if you look at the results, you see with the surface alloyed, you actually have a very high wear resistance, and compared to the as received 718. And so these are the various wear damages at various depths, coefficient of friction, and how does the wear look like. So this was essentially fretting wear analysis. He has done also similar resistance calculations against other kinds of wear mechanisms. So apart from, so as I said in the beginning, that you actually can develop, use additive manufacturing approach for refurbishment and repair, even if you are not ready to create a huge 1 meter diameter wheel or something. So some of these excavators or pulley wheels or various kinds of rotating devices, they undergo rapid wear, rapid fatigue damages, and so on. And for example, a large roll, which will cost an enormous amount of money, you don't want to throw it just because it has developed a dent or some damage somewhere. You can always refurbish that. The conventional approach used to be with weld overlay, but there you use it, you're constrained by the composition of or the availability of the filler rods, which have a different composition. Now with laser additive manufacturing, you can use the same composition to refurbish. And it's not just refurbishing, you actually can create a completely new component. So for example, this original nozzle, which has 13 parts, by additive manufacturing can be created by a single operation, varying different compositions along the thickness, along the length, and into a single part. So 13 different parts assembled to make a nozzle can be replaced by an additive manufacturing product, which is a single monolith, having the required dimension. So similar things also are applicable. I mean, arguments are applicable for other, say, for example, hydraulic cylinders or various railway wheels, wagon wheels, and so on. And also another very important scope of application is in the continuous caster rolls, which are worn very easily because of very high temperature and corrosive environments. So in that direction, refurbishment direction, the first example I want to put forward is coming from one of our former students, Dr. Gururaj Tilasam. He is now a senior scientist in one of the laboratories. So he showed that if you are worried about H13 tool steel based components, if they have undergone some severe wear, then he showed that by way of laser cladding, you actually make a reasonably thick layer and then scoop out tensile samples along the build direction or across the build direction. And you see that their tensile curves will be very similar, even better than the original curve, the original H13 tool steel material. And that's because you actually have very fine carbide, very fine martensite lathe structure or needle structure, alongside also very fine carbide distribution, carbide formation and distribution in between the laths. So because of this fine grain structure and very uniform distribution of carbides, you actually tend to have a tensile property which is even better than the original H13 tool steel. So this shows that you can see how refined the grain size is. And this shows there's enormous opportunity of additive manufacturing to produce parts which actually can show even better mechanical property than a wrought product, comparable wrought product. So Abhishek tried to create graded structures, combining 316L with 718, and produced, say, 100% stainless steel to 100% Inconel in between, varying the amount of the two components. And then he looked at the various phase aggregates that are developed and some mechanical properties and compositional distribution. This is not yet published, so I'll move on to the next work where another student, interestingly, Manish, showed that when you deposit onto the surface morphology, surface condition plays a role. In fact, without telling you much, if I simply show you these two sets of micrographs, you can easily make out they're the same material. The clad material is the same composition, same operation, but with two different surfaces, one with prior sandblasting, one with prior belt grinding. And in the process, you actually can develop such different kinds of microstructures. And you can very well imagine then the properties also will vary significantly. This is just to impress upon you that prior surface condition, apart from the powder size or the feed rate and the power density and others, may also affect the properties of the products developed by additive manufacturing. So surface topography is also an important consideration. Now, Dilip graduated with his PhD degree, and he was able to show that on this Ti6L4V alloy, you actually can improve the tribo corrosion significantly by way of surface structuring. So that means you develop certain pattern on the surface, a predetermined pattern, which creates certain molten tracks or resolidified tracks or certain other micro machine type of sedated structures, as a result of which the tribocorrosion, so combination of corrosion along with inflowing particles affecting the surface, these properties can be improved. Sharath recently got his degree, and he showed how surface melting vis-a-vis additive manufacturing can affect the properties of stainless steel, austenitic stainless steel, or Inconel 718 super alloy. So he basically first surface melted the alloy and then measured the properties. Then he did develop similar thickness structures by additive manufacturing, measured the properties and compared. And in the process, he was able to show that a very significant amount of grain refinement improves the mechanical properties, improves surface homogeneity, compositional homogeneity, and in the process also corrosion properties. So all this put together, one may argue that additive manufacturing products can actually offer you a better advantage than the conventional wrought products to some extent. Now, this is also something interesting, as I was mentioning in the beginning, that how you actually can override the thermodynamic constraints or kinetic constraints We all know that if you try to fuse aluminium with iron or aluminium with titanium or for that matter nickel or all these transition metals, they are bound to form um, uh, intermittently compounds and phases, which generally have higher melting point or higher fusion point, but more importantly, have a complex crystal structure, as a result of which they introduce high strength but very large brittle. Now, so to join iron with aluminum is a nightmare. And certainly there are different approaches using a buffer layer or a preventive layer or various other approaches. And generally, users would avoid fusion, will go for cold welding or extrusion or friction stir welding kind of an approaches. So Vidipta has been able to show that you actually can develop, you can actually fusion weld or develop iron-based alloy clad on aluminium without incurring the penalty of producing a large volume fraction of brittle phases and making the interface brittle. And the approach for that is actually very clever. So what she did was to take aluminum substrate and deposit in Rocket 401. It's a trademarked ferrous clad alloy in multiple layers. And the process parameters, the entire trick was that the process parameters were chosen so carefully that you melt marginal amount of aluminium when you deposit molten clad 401 alloy on top of aluminium. And why this marginal melting is necessary is to ensure that the alloyed zone that you form in the interdiffusion intermixing zone, the aluminum content is less than 20 atomic percent. So that you actually, even if you melt and intermix iron with aluminium, the level of aluminium is less than 20 atomic percent, so that the brittle intermediate phases don't form. FeAl or Fe2L starts forming only after 20 atomic percent level. So she was able to develop those structures, and you can see very well that first layer at various different layers, how does the microstructure change, and also the various wear properties and so on she measured carefully, and also compositional variations. So so if you look at these X-ray diffraction signatures carefully, you'll realize that in the pure Rocket 401, you have the presence of the intermetallic phases. Also in the very first layer, which is interfacing with the aluminium underlying substrate, there is signature of very little amount of intermetallic phases. But as you go to layer 2, layer 3, 4, and so on the top surface, there is no intermetallic phase. So in other words, the top surfaces can be almost like pure Rocket 401, whereas the bottom surfaces will be aluminium. So here are some mechanical properties and so on. So then Nikita worked on these continuous caster rolls and repair of that using one of these various alloys. And so these are the microstructures on the surface. And important to say that she's able to create crack-free zones. And she has recently reported some interesting results in one of the journals. Mangesh has done a similar approach, but cladding 401 on carbon steel and trying to enhance the wear resistance and service life. So this is the top clad zone. This is the base substrate, as you can see, a typical monocitic microstructure. And this is the melt penetration zone. And in the process, he was able to improve the wear resistance significantly. Then we have we have another student, Amitav. He has done a very interesting work of trying to deposit austenitic stainless steel or martensitic stainless steel on 4140 medium alloy steels and achieve a very significant improvement in wear resistance and corrosion resistance and so on. Those results I'm not bringing up here, but to tell you, I just wanted to mention that this entire work has a very large industrial relevance because in this way, Amitav wants to prove that this laser cladding approach can be a very good substitute for a hard chrome plating approach. So we are all aware that this hexavalent chromium causes a lot of concern, and it's actually banned in many countries. So this is how we can come up with a substitute for hard chrome plating by using laser as a cladding approach. So Shubhranshu is using the basically, if you have to compare these two alloys, the one with this is with chromium and this is without chromium. So he's able to prove that laser cladding allows nickel boron silicon to be as good as, in a way, better than nickel chromium boron silicon, because this nickel borides and nickel silicides, they make a very hard surface, and which actually can also make it possible to avoid making such tungsten carbide dispersed composite alloys. So with this alloy alone, we can do a lot of improvement for earth-moving equipments and prevent wear and tear. Shubhra Kamal is now a joint PhD student between IIT Kharagpur and University of Manchester, and he's currently engaged and he has published a couple of papers on first trying to understand the level of iron intermixing and dilution when he deposited Trebelloy T800. So this is basically an alloy which produces large volume fraction of Laves phases, and he is able to prove that by sacrificing certain level of Laves phases or its volume fraction, he can actually introduce a lot more toughness into the system, which is beneficial. In the interest of time, I won't go into a lot of details of these, but very interesting set of results, which are all published, and I've mentioned here where they're published. So you can see the phase analysis, the hardness, the mechanical properties, and so on. And this is how it is compositionally graded. So on the top surface, you have T800, where at the bottom you have various other levels of degrees of intermixing. It's from Taposh, who has worked on composite surfacing using carbon or graphite, and is able to produce different levels of carbides from the surface to the core, and in the process get a very nice graded structure. The last example is coming from Pawan, who is working on modeling of, this is one of the first few approaches of trying to model the thermal and compositional modeling of powder feeding system. This is on a powder bed system, and is currently, so one can produce actually on the surface and along the cross section the various temperature zones, thermal profiles, and the corresponding thermal history like cooling rate and thermal gradients and so on. And he's trying to correlate with the microstructure. So with this, I would like to come to the conclusion, saying that the additive manufacturing essentially is a droplet integration process, and it can build 1, 2, or 3-dimensional products, components, devices. It has a huge market potential. As I said in the beginning, it's growing very significantly, and far from saturating, there are enough number of scopes of doing some innovative work, but and that innovation will concern the composition, size, morphological changes, and we have. But as I said, we need to understand the long-term effects in terms of deformation behaviors, fatigue creep, or reliability, and assess the various failure modes, and then compare with the conventional rod products and see which way they are actually better. So opportunities are huge. There are hurdles, and we need serious efforts to overcome them. So with this, I would like to conclude acknowledging all the group members, Josna Datta Majumdar, Gopal Roy, and students who have worked with us at various stages, and also the collaborators within the department and outside, Siddhartha, Shibrat, Kaushik, Indrani, Chandrasekhar, Sumant, and so on. Thank you very much. Thank you.
Yeah, thank you, Professor Manna, for such a nice and wonderful talk. Since it's already 2 o'clock, any quick questions from the audience?
I took a little longer than I.
Yeah. Also, sorry. Great. If no, yeah. Narges Tabriji, please.
Hello, thank you so much for your great presentation. It was really useful. I have 2 questions. Have you done any project about single crystal superalloy? About the repair, for example, the blades that made of single crystal?
No, not in our group at Kharagpur, but we did some trials elsewhere. I can share my experience with that. When you have a single crystal of large dimension, and when you deposit a metallic layer on top of it, there is very little chance that you can maintain the same orientation, exactly the same orientation. In other words,
yes.
When the liquid solidifies on top of a solid substrate, there will be an interface, and across the interface, you'll have tiny little grains. But the advantage is, because of fast cooling, you may retain nearly the same orientation. In other words, the interface you form need not be a large angle boundary. In all probability, it will be a low angle boundary and a directionally grown crystal. So if one argues that, I possibly will not be able to maintain a single crystal, I will say yes. But at the same time, I will also have a counter-argument and saying that this is not going to altogether make the single crystal configuration completely redundant. You will be able to retain low angle boundaries and repair.
Okay, thank you. And just another question about your interesting work about GD as a coating. I mean that gadolinium. I don't know that. Have you done any test about this coating compared to the common coating as a zirconia, about the breathless or toughness about this coating? Because I guess that it should be lower than zirconia.
The main of thermal conductivity and was that in addition to reducing the thermal conductivity, the addition did not, in other words, bearable, and in a way better, because I forgot to, in the interest of time, I didn't mention, because of substituting a tetravalent with a you're likely to produce point, and these point defects not only reduce the conductivity but also helps in creating some kind of a cushioning effect, which means that if there's a crack, the crack will find it difficult to propagate if it finds a pore ahead of it. So the sharp notch gets blunted. So the adhesion, the adhesive strength is improved, not very significant. One bending to show that adhesion is acceptable.
Okay, thank you so much. Thank you.
Thank you.
Thank you. One quick question from my side. You mentioned in the initial slides that there is no wastage at all with additive, but going with recycling after using these powders for 8 to 10 cycles, you end up with a lot of issues. So aerospace industry is going to reuse them. Any idea?
Zero waste is sort of a no-brainer, because there's no manufacturing that can happen without ultimately you can scoop the last drop of. So, but this is bare minimum. Now, of using a wire better. In fact, I would say a wire machine is probably a much more effective means of additive manufacturing than powder bed fusion.
Thank you so much. Since it's already 4:05, so thank you very much, Professor Manna, for your nice talk and visiting us here at WMG. And for joining the talk. Have a nice afternoon. Bye-bye.
For your attention, results to you.